So today the remaining slide is just 10 slides. We talk about noise in FM modulation. Of course, when we talk about FM, the PM is part of the FM modulation as well. So both of them are in one family. Okay, so we know what is noise. So in fact, noise generated by lightning, motors, automotive ignition system, power line switching systems. So those are noises. So, and typically they are narrow spikes of voltage, and usually they have high frequency because they have very short time duration. And the noise will be added to our signals and then interfere with them. Sometimes they can be very severe and damage or change the whole information of the noise, the message. So this is an example of noise added on a frequency modulated signal. So you can see the black spikes on the modulated signal. So the amplitude is just added to the available, modulated signal. And those will make some noise if it is voice, for example, or if it is other data can interfere. So, but unlike AM, which is highly amplitude dependent, and the amplitude is important, in FM, the amplitude is less important because the information of the message is not in the amplitude. You can see the amplitude of the FM is constant and not change. So then noise can be removed a little bit easier in terms of amplitude. So let's see what I have in my text. Yeah, FM have a constant modulated carrier amplitude. So FM receivers contain limiter circuits that deliberately restrict the amplitude of the received signal. So means they cut the amplitude of the signal to make sure there is no higher amplitude than the carrier or the modulated signal. So any amplitude variations occurring on the FM signal are effectively clipped by limiter circuits. This amplitude clipping doesn't affect the information content of the FM signal, since it is contained solely within the frequency variation of the carrier. So as we said, the message, the information of the message is not in the amplitude. It is in the frequency. In fact, one of the primary benefits of FM over AM is superior noise immunity. So is more robust in terms of noise. So AM is more sensitive to noise compared to FM. So that is what we have seen just now here. You can see we can easily remove the amplitudes. The amplitudes higher than the amplitude of the modulated signal, So then noise, if they are higher in amplitude, will be removed. So the remaining is frequency noise, because some noise have high frequency. So that is something which we can discuss now. We have something we call pre-emphasis. So most of modulating signals like voice, they contain low frequency. But there are some signals like musical signals. So they have high frequency elements and high frequency harmonics. And those high frequency elements or harmonics, usually they have low amplitude. So means their amplitude are small. So you can hear musics, some high frequency elements could have very low amplitude. So noise is primarily, as we see, sharp spikes of energy and contains a lot of harmonics as well, and can be larger in amplitude than the high frequency elements in the modulating signal. So meaning that if we have high frequency noise and their amplitude is larger than the amplitude of our message signal, like musical message or signal, then the noise can interfere with our high frequency elements. So because the amplitude is larger and they can affect on the message signal. To overcome high frequency noise, a technique known as pre-emphasis is used. What is pre-emphasis? Is a high-pass filter placed at the transmitter side. The message signal will pass through this high-pass filter before it is modulated. What does this high-pass filter do is it amplifies high-frequency components more than low-frequency components. So this is the circuit. So it's like a RC circuit. So the modulating signal will be applied to this high-pass filter. Then it goes to be applied for frequency modulation, and then it will be transmitted. I will show you after this. Yeah, here. This is the pre-emphasis response, frequency response. Means the low frequency element, the x-axis here is frequency, the y-axis is amplitude. You can see the response. In the low frequency, the amplitude is low, and then somewhere after around 2000 hertz, the amplitude increasing up to some level. After that, it cannot increase anymore the amplitude, so it remains constant. So this slope of increasing amplitude in the higher frequency is in fact a gain happening in the high frequency amplitude. And then our message will be a little bit modified, but that modification later, when it reaches to the receiver, will be compensated and return it back to its normal condition. So just whatever we do in the transmitter side, something opposite to this will be applied in the receiver side, something that you can see in the right side graph. There will be an opposite filter, which is low pass filter. We call it de-emphasis. So low frequency element will experience no gain and just remain as a flat response, but higher frequency element experiencing some attenuation. This attenuation is just opposite to the what we gain at the transmitter side. If you look at both effect, combination of the pre-emphasis and de-emphasis in the graph at the bottom of this slide, where my mouse is showing, you can see a combined frequency response is just like a flat response. So means the manipulation applied on your message signal at the transmitter will be compensated back in the receiver side, and your message remain the same. So yeah, the de-emphasis is a simple low-pass filter, can operate as a de-emphasis circuit in the receiver. So this circuit returns the frequency response to its normal flat level. The combined effect of pre-emphasis and de-emphasis is to increase signal-to-noise ratio for the high frequency components during transmission, so that they will be stronger and not masked by noise. So that is how we can solve high frequency noise issues in FM modulation. And this is a simple low-pass filter, which is also a RC circuit, low-pass filter for de-emphasis circuit. So these two equations shown here, this equation is in fact for high-pass filter. You have R1, R2, and the C to calculate what is your cutoff frequency for higher frequency part. And this is for the low-pass filter, in fact, can be also applied to know the cutoff frequency from where the gain going to be increased or gain to be decreased, or in fact the attenuation to be started. So that is two equations. So this equation will be used more when we want to work with the circuits, but it is not within the objective of our course to work on these circuits very much. Okay, so the last part of our topic is compare advantage and disadvantage of FM against AM. When we say FM, it is also applied to PM as well, because they are quite same frequency, modulation. In overall, FM offers more significant benefits than AM. But of course, AM also has its own advantages. The main advantage of FM and PM are they have superior immunity to noise, made possible by Clipper limiter circuits in the receiver. So this is the main advantage, as we mentioned. Second is, in FM, interfering two signals with the same frequency, let's say you have two voice channels and they interfere together, the signal with lower amplitude So lower means if there is 1 dB amplitude difference between the two signals, the signal with lower amplitude will be rejected. This is known as capture effect. But of course, if they are exactly the same level, so then they make some problem. But if they have the other channels, which is side effect, we expecting those have lower level than our main channel. So maybe they are fading effect, coming reflected some frequency from elsewhere to our channel. So then, of course, they should have same frequency, otherwise they won't be interfering. And if they have lower amplitude, they will be easily rejected by the system. System will take the higher frequency one. But if this is applied in AM, they will be just superimposed and you can't remove them. There is no way in AM to remove your amplitude noise. So, but you can remove frequency noise easily in AM, but not amplitude. Yeah, that is another advantage of FM against AM. FM signals have a constant amplitude, and there is no need to use linear amplifiers to increase power levels. Linear amplifiers usually have more noise content and they have less efficiency. You need to use them for amplitude modulation. So, but for FM, those are not very necessary because the amplitude is not very important for frequency modulation. For AM, we need to have super high gain, so to make sure easily detect the amplitude for AM. So that was the advantages of FM. In terms of disadvantages, so FM uses considerably more frequency spectrum compared to AM. So most FM communications are at some frequencies which we have sufficient bandwidth available. So that is not used for other applications. Those are VHF, very high frequency, ultra high frequency, and microwave frequencies. So that is because they use high bandwidth compared to AM. They mainly designed to be, decided to put in those range of frequency, very high frequency ranges, which not very maybe applicable for other application or not very crowded in terms of demand for other applications. FM, so this was one of the disadvantage of FM, which they need more bandwidth. The second disadvantage is they use more complex circuits for modulation and demodulation compared to AM, which is quite simple circuits. And although this complexity of FM and also PM has been solved by development of ICs, so today's these are less important in terms of disadvantage, but still, of course, their system are complex, but the ICs are available with almost comparable price as AM and easy to be used. FM and PM have become the most widely used modulation methods in electronic communications today. So they are quite popular. Of course, AM also is. FM and PM also they are. So in many advanced modulation techniques, PM always is one of them. So is always available. So these are some applications of AM and FM. So many of those we have discussed earlier maybe. So AM broadcasting, of course, is AM. FM broadcasting radio, of course, is FM. FM stereo multiplex sound, they use double sideband AM and FM. TV sound is FM. TV picture use AM, vestigial sideband. So TV color signals use quadrature, double sideband AM. Cellular telephone, they use FM, FSK and PSK. Cordless telephone, they use PSK and FM. Fax machine, FM, QAM, AM plus PSK, which is QAM in fact. Aircraft radio use AM. Marine radio use FM and single sideband AM. So and so on. So you can see both AM and FM, they have their own applications. So this OOK refer to also AM, or they are ASK. So yeah, that's all for my topic of lecture today.